Hi, I'm Shuhei Imai, graduate student at Tohoku University in Japan. I'd like to talk about my research in this title, improving pronunciation clarity of Dysarthric speech using CycleGAN with multiple speakers. First, I'll talk about my background. The main topic in my research is dysarthria. Dysarthria is a disorder that cannot be pronounced correctly like a healthy person. So the voice of people with dysarthria are difficult to hear. This causes a fatal problem in their daily life. For example, it can be difficult to listen to and understand the presentation of them, and also difficult to carry on the conversation. Therefore, a method of support for people with dysarthria has been proposed. First is speech therapy with a speech language pathologist. This is a method for people expected to improve with training, so it is used for people with relatively minor symptoms. For those with severe symptoms, another method can be considered. Application of text-to-speech and voice conversion techniques. When using text-to-speech, the patient first enters text into the system. The system converts the text into easy-to-hear speech, similar to that of a healthy person. On the other hand, in the case of using voice conversion VC, Dysarthric speech is input to the system. The system converts the speech into an easy-to-hear speech while preserving the content. In recent years, various methods based on VC have been proposed. As a method based on voice conversion, Patron is one of the most representative and high-quality methods. This method combines attention-based model with a phoneme recognizer. In the paper, it was shown that it achieved high score for naturalness and intelligibility. However, this method requires 13.9 hours of dysarthric speech. For people with dysarthria, speech is heavy burden. Therefore, the cost of data collection and learning is very high. Ideally, it is desirable to reduce the cost of data collection of dysarthric speech while maintaining the quality of pattern. With problems of previous slide, our purpose of this study is proposing a high-quality method based on VC using small amounts of dysarthric speech. To achieve this purpose, ideas are shown below. VC methods including pattern normally requires paired speech of source and target speakers. Applying a voice conversion that requires paired dataset makes difficult to improve quality due to amount of datasets for training and misalignment. In order to solve this problem, we apply CycleGAN-based non-parallel VC method. Also, using the non-parallel VC method allows us to use large healthy speech dataset. However, since the dataset is usually uttered by a single speaker, creating a large healthy speech dataset is also costly. So we consider using multiple speaker speech as a healthy speech dataset. Next, I'll explain about ideas of our proposed method in detail. Please consider the case in which only a small amount of dysarthric speech is available. Previous method that requires paired speech datasets during training. Basically, the previous method requires the same content in both dysarthric and healthy speech. For example, a person with dysarthria and a healthy person each read "It's a call today" and then they are aligned frame by frame to perform a one-to-one voice conversion. Therefore, the previous method requires the size of the datasets for dysarthric and healthy speech as the same. If only a small amount of dysarthric speech is used for training, the amount of healthy speech is also small, depending on it. This will result in a decrease in quality. On the other hand, the proposed method does not require paired speech. Therefore, we can train with a small amount of dysarthric speech and a large amount of healthy speech. Also, in the method proposed before pattern, it was necessary to align the frame of dysarthric speech with that of healthy speech using dynamic time warping. Since the speed of dysarthric and healthy speech is quite different, it could not be performed properly, resulting in serious quality degradation. However, the proposed method can solve this problem. because it is based on non-parallel VCs and does not require alignment. As mentioned in the previous slide, proposed method allows us to use large healthy speech dataset. However, since a dataset is usually uttered by a single speaker, creating a large healthy speech dataset is also costly. So, we consider using multiple speaker speech. We create a large dataset by combining small amounts of speech of each speaker. This makes it easier to create large datasets. Also, in the case of multiple speaker conversion, it is expected to convert to average speech, which contains less speaker identity. This may result in specialized conversion to achieve the pronunciation clarity of healthy people. Next, I'll explain generative adversarial networks, so-called GAN, which is an important elemental technology of the method. GAN consists of two models, generator and discriminator. Generator G learns to generate fake data that fools the discriminator. On the other hand, discriminator D learns to distinguish the real data from the data created by generator. These two models are optimized by competing with each other. The update process is as follows. First of all, before the D update, D cannot distinguish the real data from the fake data created by generator. Therefore, update D so that D can distinguish fake and real data. This makes the data produced by G cannot fool D. So, we then update G to create the fake data that D cannot distinguish from real data. By repeating these updates, G will be able to create fake data similar to real data. CycleGAN is a derivative model of GAN, which uses two sets of GAN. This enables style conversion between non-paired datasets. For example, you can convert a picture of a monet into a photographic image, or only a zebra into a horse from a picture of a zebra. CycleGAN VC2 is one of the most popular methods of non-parallel voice conversion, and is a method of applying CycleGAN to VC. This method can learn to convert between datasets with different speech content. For example, this source speaker dataset and this target speaker dataset do not contain a one-to-one correspondent speech. However, CycleGAN VC2 can convert the source speaker speech to the target speaker's speech, even in this case. Therefore, the cost of creating dataset is very small. The conversion process is shown below. First, analyze the source speaker speech and extract acoustic features, fundamental frequency, mercapture, and periodicity because of using word for speech analysis and synthesis. Next, only mercapture is converted by generator. Finally, the speech converted to the target speaker is synthesized by word. Also, the network structure looks like this: generator and discriminator. The important point is that they consist of a convolutional neural network that performs convolution in the time direction, so they can convert considering the time structure. Next, I'll explain about overview of proposed method. Proposed method learns the conversion from Dysarthric to healthy speech based on CycleGAN VC2. So the flow of the conversion is the same, but the input and the output are different from CycleGAN VC2. As a healthy speech dataset, we consider the single speaker and multiple speakers case. Therefore, we need to check whether the performance changes by using multiple speakers. From the above, in this presentation, we evaluate how the use of multiple speakers as a healthy speech datasets results in performance in the proposed method. The datasets used in the experiments is shown below. As datasets of Dysarthric speech, we used a male patient speech with amyotrophic lateral sclerosis. For the training, we used 868 sentences, 1.3 hours of speech. This is less than 1/10 of the data volume of pattern. For the test, we used 10 sentences. On the other hand, as a healthy speech dataset, we created 4 datasets for a different number of speakers. Therefore, 4 models were trained using a Dysarthric speech dataset and 4 healthy speech datasets. As the total number of speech used for evaluation is 40 sentences. This is an experimental condition. We used the same network architecture described in the paper of CycleGAN VC2. The following hyperparameters were also based on the paper. We conducted the subject evaluation of the 2 items, pronunciation clarity and speech quality. In the evaluation of pronunciation clarity, subjects score the clarity of Dysarthric of speech pronunciation. Also, in the evaluation of speech quality, subjects score how close the speech is to real speech. As subjects, 10 native Japanese speakers recruited through crowdsourcing were selected. We instructed them to use earphones or headphones in a quiet environment when participating in the experiment. Also, in the experiments, 40 converted speech were randomly played. Now, I'll explain the result of pronunciation clarity. Despite the 60 healthy speaker datasets having less data amount than that of single speaker, the model trained with 60 speakers got a higher score. Therefore, it is confirmed that using multiple speakers as a healthy speech dataset can improve pronunciation clarity more effectively than single speakers. Also, using multiple speakers for a healthy speech dataset, the results of 60 and 120 speakers are almost identical. So, it is confirmed that there can be no improvement in pronunciation clarity with more than a certain number of speakers. Next, I'll explain the result of speech quality. Comparing the mean opinion score and the size of the dataset in these 4 cases, we can see that the score is proportionally higher with the size of the dataset. Unlike the result of pronunciation clarity, the mean opinion score of the model trained with single speaker was higher than that of the model trained with 60 speaker. And we could not confirm the effectiveness of multiple speakers. Therefore, it is thought that a larger corpus of healthy speech can improve speech quality. In concluding this presentation, we propose a method converting Dysarthric to healthy speech using non-parallel VC based on CycleGAN VC2. Subjective evaluation showed that using multiple speakers as healthy speech dataset improved pronunciation clarity than using a single speaker. And also speech quality is improved depending on the healthy speech dataset size, not the number of speakers in the dataset. These results show that the use of large corpus of multiple speakers as healthy speech dataset is effective. As future work, first of all, we are going to conduct a comparison experiment with the previous methods. Afterwards, we will conduct experiments to improve performance. That's all for my presentation. Thank you.